Hello students, in this session we are going to look at radiation. Radiation is one of the ways in which heat is transferred. The other two modes of heat transfer we all know, conduction and convection. So radiation does not really require any medium. The energy that we get from the sun to the earth comes through vacuum, right? There is nothing between the sun and the earth, and still we are able to receive the heat from the sun. So all the heat that we get from the sun to the earth is in this form. So here's an example. There's a man sitting and here's a room heater. Now think about how does the room heater heats the entire room. Most of the heat transfer is through radiation, although in this case some of the heat transfer is also through convection. Convection requires a medium like air or water to travel. Whereas radiation does not require any medium, because radiation travels in the form of electromagnetic waves. And we all know that electromagnetic waves do not really need any medium to travel. Now, how much heat is being transferred? Let's quantify that. In radiation, what is the heat current? Heat current is represented by this Q here. Q, small q, is the heat current. It's the amount of heat flowing from a given surface in a given amount of time. That's the heat current, okay? If there's a very small amount of heat flowing through a very small time interval, the heat current would be represented by dq upon dt. Whatever this is, whether it's a large heat flowing for a large interval of time or a small amount of heat flowing for a small interval of time, the heat current is being represented as small q. Experiments were done, and it was found out that the heat current actually depends on a lot of factors, where the heat supplied or the heat emitted from the surface basically depends on the temperature of that surface. So here we have two things. One is this surface. Ts is the temperature of the surface. Whereas this thing that you see, this is the surrounding, okay? And T surrounding is the temperature of the surrounding. What we have written here, this expression, is the net heat current. So it's the heat coming out of the surface minus the heat absorbed by the surface. That is what is written here. So if you want to write it in parts, what is the heat current flowing out of the surface? So heat current out of the surface. That is given by emissivity of the surface. We'll talk about what is emissivity into the area, the surface area of the given surface. Stefan-Boltzmann constant. Stefan-Boltzmann constant is this sigma, and this is the value, okay? And the temperature of the surface in question, because we are talking about heat flowing out of this surface, so we'll take temperature of the surface to the power 4. This is the heat given by the surface. This is the heat current out of the surface. This is heat current flowing out. Remember, this is our surface in question, okay? And what is the heat being absorbed by it? Or what is the heat current inflow? Heat current flowing into the surface. Now that would depend on the surrounding temperature, not the temperature of the surface. So Q being absorbed by the surface, or the heat being absorbed by the surface per unit time, which is the heat current coming inside, is epsilon, which is the emissivity of the surface, area, Boltzmann constant, Stefan-Boltzmann constant, temperature of the surrounding this time, but again raised to the power 4. And that's why the net heat flowing out of the surface is Q out minus Q in. And when you do that, you get Q. So Q net is equal to Q out minus Q in. So this is the net outflow of heat per unit time, or the net heat current for this surface in question. Okay. Now, let's take a look at all the elements. What are these things? What is this epsilon emissivity? Also known as surface emissivity, it characterizes the surface in question. So if the surface is a perfect absorber of heat, it is also a perfect emitter of heat. In such a case, emissivity is 1, and such surfaces are called blackbody surfaces. If the emissivity is 1. Now, there is nothing like a perfect black body. Something very, very close to a black body is a black hole. Emissivity 0 means something which does not absorb any heat at all. Even emissivity 0, there are no real objects that have emissivity 0. You would find objects that have emissivity close to 0, something like 0.03, 0.04, or so on. So we have a range of objects whose emissivity varies from 0 to 1. Okay, so emissivity of the object or the surface varies from 0 to 1. 0 means it does not absorb heat at all. 1 means it's a perfect absorber of heat or a perfect emitter of heat. So we understood what is emissivity. A, we all know, it's the surface area. It's the area exposed to the surrounding. It's that area we are considering, okay? This is a constant. We've seen its value here. The unit you can find out based on this formula. Ts is the temperature of the surface in question. We might have, sometimes in some questions, we might have a metal ball. Sometimes we might have a red hot cube, iron cube. So we'll take the temperature of that red hot iron cube. And T surrounding would be mostly your ambient temperature. If you're on Earth, the ambient temperature, whatever it is, wherever you are. If you're on some other planet, for imagination's sake, if you're on some other planet, the surrounding temperature might be different. So if we understand how we get this, let's now apply all this understanding into a problem which came into JEE this year itself. Let's take a look. Here's the question now. It says there are two spherical bodies of same material. Same material means emissivity is going to be the same for both, having radii 0.2 meters and 0.8 meters. So radius of the first one, 0.2 meters, radius of the second one, 0.8 meters, all right? The temperature of the smaller body is 800 Kelvin. T1 is 800 Kelvin. Remember, whenever you are using this formula, take temperature in kelvins alone, okay? And then temperature of the bigger body is 400 Kelvin. So if the energy radiated from the smaller body is E, what is the energy radiated out of the bigger body? Or what is the energy radiated from the bigger body? And we have to assume that there is no effect of surrounding. So all the heat current will be only because of heat current flowing out, nothing flowing in, because we're considering that the surrounding has negligible effect. If we understand the question, let's write the expression for E. E is emissivity, surface area, Stephen's constant, and temperature of the smaller body, which is T1 to the power 4. This area would be, of course, the area of the smaller body, A1. Emissivity is the same. We'll just keep it E. Sigma is sigma for both the bodies, so we'll just keep the symbols. A1, the surface area, the outer surface area. Since it is a spherical body, it's going to be 4 pi r square, right? So 4 pi r1 whole square into T1 to the power 4. T1 value, we know T1 value is 800 kelvins. We'll put that later, okay? So the energy radiated by the bigger body, this is what we have to find. So E bigger, this is going to be epsilon area of the second, of the bigger body, the surface area of it, Stephen's constant, temperature 2 to the power 4. Let's find their ratios quickly. E big upon E. Epsilon A2 sigma T2 whole square, T2 to the power 4, sorry, upon, so epsilon A2 sigma T2 to the power 4 divided by epsilon A1 sigma T1 to the power 4. Sigma, sigma, epsilon, epsilon cancels out. In A2 upon A1, we're going to have R2 square upon R1 square. And here we have T2 to the power 4 upon T1 to the power 4. R2 upon R1. Let's check that out. What is R2 upon R1? So the second radius is 0.8 and the first radius is 0.2. So R2 upon R1 is 0.8 upon 2, that's 4. So we have 4 squared multiplied by T2 upon T1. Well, T2 is smaller than T1. So we have 400 by 800. That is 1 by 2. But this is raised to the power 4. You solve this and you get the value here, and then you'll get the answer. 16 multiplied by 16, this gets cancelled, and what you get as this is the answer. Okay.